Thank you very much, Vincent, for the kind invitation. Also to Bowen and Simon. It's really a pleasure to be here with you today. Hello, everyone. I hope you're all doing great, that you had a nice extended weekend and let's say a nice productive day. So my name is Oussama Er-Raji. I'm a PhD student at the University of Freiburg, that's Fraunhofer-Isar, and I'm delighted to talk to you today about our recent efforts in advancing industry-compatible perovskite silicon tandem solar cells. In what way? In the fully textured pathway. Now, when we try to make perovskite silicon tandems in order to, let's say, go beyond the efficiencies that we can get with standard silicon single junction solar cells, there are multiple architectures that we can choose from. So here you can see so here you can see the different architectures that we have. We have the planar perovskite silicon tandem, which is based on the fact that we have a planar silicon substrate on which we spin coat the perovskite absorber. We have the buried architecture, where again we use solution processing, but here it's done on top of textured silicon with a relatively small pyramid size in a way that the thick perovskite absorber really submerges the textured silicon and the top surface is flat. And then we have the fully textured architecture where the perovskite film actually conformally coats textured silicon with a pyramid size which is larger than 1 micrometer. Now, the fully textured architecture is really interesting from multiple perspectives. First, it allows us to use an industry-compatible silicon subcell, which is why the title of the talk is actually Industry-Compatible Perovskite Silicon Tandems, because we're really using something that already existing silicon production lines are producing. And therefore, we are, let's say, as close as possible to industry, which will, of course, reduce the costs when we try to make this technology as a commercial product. And secondly, the fact that we have this structured interface here at the top allows us to reduce the reflection losses. And as such, a lot of simulation studies have recently shown that in a module, one would get the highest energy yield for this tandem solar cell architecture. Now, how do we make the perovskite absorber in a way that it conformally coats textured silicon? Well, researchers have found that using the standard one-step solution spin coating does not really yield to a conformal film coating. As you can see here, we have the pyramid tips which are uncovered. Instead, in 2018, a collaborative effort between EPFL and CSEM came up, or let's say laid the ground or the foundation for the hybrid method. So what is the hybrid method? It combines 3 different steps. In the first step, the inorganic precursors of the perovskite, so lead iodide, for example, and cesium iodide, are evaporated in order to form a conformal inorganic scaffold or template on top of textured silicon. So typically we use lead iodide and cesium iodide, but also some other researchers use cesium bromide. And in terms of the rates, usually we have here 1 angstrom per second, and here around 0.1 angstroms per second, so around 10% ratio. And in the second step, we infiltrate the organic parts of the precursors, or let's say of the perovskite precursors within this scaffold. So you can think about this as a sort of sponge that will absorb these organic precursors. And after an annealing step, we have a conformal coating on textured silicon. Now, as you can see, there are really 3 different steps, and for every step, there are a lot of parameters. So it opens up, let's say, the space for a wide parameter variation, and every parameter can play a critical role in the final perovskite film. This is not the only challenge. So let's imagine that now we solve the challenge of understanding how perovskite forms well on textured silicon. We then have also other challenges in the cell, such as designing and finding suitable charge transport layers that can really conformally coat textured silicon, and also designing and having conformal passivation strategies on the increased surface area of the perovskite absorber. And these will be the 3 axes that I will try to cover in the talk of today. So first, I propose let's look at how to control the perovskite film formation with the hybrid route. And to make it a bit easier, we will only look at the method on planar substrates in order to remove any, let's say, issues that can come from textured substrates. This we will look at in a second place. So one of the important things that we always have to ensure when making perovskites with the hybrid method is to have a good balance between the inorganic precursors in the first step and the organic precursors in the second step to have a stoichiometric perovskite film. And one of the issues that we often see is that we don't have a phase pure perovskite. As you can see here in the XRD, we have a high intensity of the lead iodide peak that can be also seen in SEM at the interface. And of course, this insulating material can lead to issues in charge extraction, in particular hole extraction if we have a PIN perovskite subcell. Now, we thought that the issue might come from the fact that we do not have enough A-side cations at the buried interface that could participate to the, let's say, formation of a perovskite crystal structure. And to test whether this is true, we then tried to increase the amount of cesium in our perovskite, and this we can do just by increasing the amount or the rate of cesium iodide that we evaporate in the first step. So what happened when we tried this, as you can see, going from 10%, so cesium iodide here is 0.1 angstrom per second, here we go to 0.12, and here 0.15 angstrom per second, you can see that we can gradually, slowly but surely, reduce the amount of lead iodide in our film. How does this reflect in terms of the optoelectronic and the photostability of the film? We carried out photoluminescence measurements, and here we see the evolution of the PL peak position and the PL peak height over the duration of laser illumination. So you can see that when we have a high cesium amount, so for example here the curve in blue, you can see that under light illumination or under laser illumination, there's a high deviation of the PL peak position, which shows us that we have halide segregation and our perovskite is not photostable. So the high, and on the other hand, when we have a low cesium amount, we have a more stable PL response. So here we can see that cesium not only impacts the conversion level, so the conversion from inorganic scaffold to perovskite, but it also plays an impact and a role on photostability, and this should be taken into account. So based on the fact that we have not a very good photostability at high cesium, we thought that we will stay with this amount of cesium, a low cesium of around 10% compared to lead iodide, and we would then increase the other cation in the system, which is formamidinum. And the formamidinum can be increased by just raising the amount of organohalides in the second step, so by increasing the concentration of the solution in the second step. And so here you can see that by going from the reference 0.45 molar gradually up, we can really eliminate this lead iodide peak and have a fully converted perovskite. So you can see this better in the SEM, where now we do not see anymore this lead iodide here at the interface. And when looking at the elemental composition of the different elements composing the perovskite, we can see really that throughout the depth we have a, let's say, a homogeneous elemental composition. Now we solved one issue, but we also observed another issue, which is the fact that we have a lot of grain boundaries. And this again will have an important, let's say, contribution on the transport of charge carriers within our absorber. How did we find a solution for this? Well, we observed that in the hybrid method, the annealing temperature can really play a big role on the size or on the large apparent grain size formation of the hybrid process perovskite. So here, for example, you can see that by going from 120 degrees up to 165 degrees, we had an increase in apparent grain size. Now, the annealing temperature in general, and also, let's say, the annealing strategy plays really a big role on the dynamics of the perovskite crystallization. And to get a bit more insights about how to control it, we carried out an in situ XRD study. So in the first step, we evaporated the scaffold, then we infiltrated the organics in the second step, and then we directly took our sample and went to an XRD machine where we placed our sample, closed the chamber, set a certain humidity, and then varied the annealing temperature and saw how the phases change and evolve during the crystallization. So here we will see how the perovskite main peak and the lead iodide precursor peak change depending on the annealing temperature and the time. At 120 degrees, you can see that the lead iodide peak that comes from the precursor is very high at the beginning of the annealing time. But as the annealing time goes by, we have the reaction going, and therefore the lead iodide intensity, or let's say the reaction happens, and we, in around 7 minutes, we have a full conversion from the lead iodide phase to the perovskite phase. When we increase the annealing temperature, or let's say also here you can see that the perovskite peak then starts to increase. And then what happened when we increase the annealing temperature is that the amount of lead iodide that we detect at the beginning is much less compared to that at 120 degrees. So this shows us that already we have a speed that's taking place. So the crystallization becomes a bit faster. And the full conversion happens in less than 5 minutes compared to 7 minutes or a bit higher at 120 degrees. And secondly, we see again that with the annealing time, the perovskite peak increases until stabilization. When we now go to 150 degrees, we observe that the reaction is even faster. Only 2 minutes are enough to have a full conversion of the lead iodide phase, and again, a similar pattern for the perovskite peak. So this really shows us that annealing temperature can play a role in regulating the speed of crystallization. The second thing that we can see is that the higher the annealing temperature, the higher was the stabilized value of the of the perovskite peak. So this also shows us that the annealing temperature can play a role in terms of regulating the film crystallinity of our perovskite. Now, what happens if we go even to a higher temperature, so 165 degree, we see that a bit similar pattern with the perovskite, but here we see that the lead iodide peak does not go to zero, which shows us that above a certain temperature, the organics become highly volatile. They do not diffuse within our inorganic scaffold, and therefore this again gives us the issue or raises the issue of the full conversion. So it's very important to optimize the temperature, and from this experiment we can see that 150 degrees is really an optimum between high crystallinity and large grain size, but also full conversion. And this might also explain why in literature you will usually see that people use 150 degrees as an annealing temperature. So now that we have seen a bit what are the impact of different process parameters on the perovskite film quality with the hybrid method, what happens if we go and put this film in a fully textured tandem? So this will be the second, let's say, part. So here we played, or let's say we directly placed the perovskite film in a PIN perovskite top cell where we had 2 packs and C60 as charge transport materials, and we had the silicon heterojunction as a silicon subcell. And when we first measured these devices, we actually observed a large hysteresis between forward and JV curve, and we observed that we had a severe S shape. What was interesting to also observe is that once we kept the cell under illumination for a period of around 3 hours, the hysteresis completely was resolved, and we had a much improved fill factor and VOC. So to see this a bit better, here you can see the fill factor, the VOC, and the JSC over time. And here you can see, let's say, when we keep the cell under light illumination, how the fill factor changes. So here you see the fill factor taken from a reverse JV scan and forward JV scan, and in between the cell is kept at 1 sun illumination under open circuit conditions. So you can see that we can gain actually more than 10% absolute in fill factor, and then there is a stabilization. And in terms of VOC, we can gain up to 300 millivolt in VOC, which is really just enormous. And this actually was a reversible process. So if we kept the cell in the dark in a storage and then remeasured the cell once again, we observed that the efficiencies went down and then went up again under light illumination. And this led to around 7% change absolute in efficiency due to this light soaking phenomenon. Now, this light soaking phenomenon is really bad for multiple reasons. First, dynamic changes have been shown to, let's say, induce long-term degradation issues in perovskite solar cells, but also having a batch with 20 cells and needing 3 hours to measure every cell is not really pleasing. So in order to understand a bit more where this light soaking phenomenon is coming from, we looked a bit at literature which was in, let's say, shown for perovskite solar cells where light soaking has been demonstrated. And there were 3 main reasons. The first one was light-induced lattice expansion, where researchers have found that there was a direct relationship between the VOC and fill factor change during the illumination time and the lattice parameter, where during illumination, the lattice parameter would increase, then inducing a light-soaking effect. Other researchers have found another reason, which is healing of non-radiative defects, where under illumination time, the density of defects was reduced, which can be reflected here in an increase of PL intensity, which then also matched well with the increase in VOC. And the third reason, which was put forward in literature, is that of ion accumulation at the interface. To test which one of these, let's say, reasons was that related to our case, we tested all of them. So first, is it a healing of non-radiative defects? So by monitoring the VOC and the PL peak intensity over time, so around 3 hours, we see that there is a non-proportional relationship. So it's not healing of non-radiative defects. Secondly, is it light-induced lattice expansion? We measured XRD before light soaking and after light soaking, and by looking closely at the full width half maximum of the perovskite peak, we observed that actually there is no increase in lattice parameter size. Finally, we also had some doubts that it might be a defective HTL, because at the time we used 2 packs with a very high concentration of 7 millimole, which was 7 times higher than that used in the literature. And here, by using nickel oxide 2 packs with a low concentration of 2 packs, or even a different family of HTLs, such as evaporated TETM, we observed a similar, let's say, result, which shows us that it's really none of these 3 reasons that can explain the light soaking phenomenon in our cells. So then we turned our attention to mobile ions. And in order to estimate the mobile ion density in our device, we use the technique that I think will make Vincent very happy. So it's the bias-assisted charge extraction measurement, where let's say we can get an estimation of the mobile ion density by making 3 steps. First, we have our cell in an open circuit-like condition, where then we switch to 0 volt. And when we do this, all the carriers present in the device get extracted. And depending on the extraction time of the different charges, we can attribute them either to a capacitive charge, injected charge, or ionic charge. And in this region, so of slow, let's say, a millisecond regime, we can get then an estimation for the mobile ion density that we have in our device. So we carried out such a methodology, and we took a reference case where we had a cell with spin-coated perovskite, and then the cell with the hybrid method on textured silicon. In the reference cell, we observed that the mobile ion density was relatively low, so in the order of 10 to the power 15. But then when we measured it on a textured cell, we observed 2 times higher order of magnitude, so 8 times 10 to the power 17. And this we linked to the fact that we did not have, at least in the first tries of making perovskite films on textured silicon, we did not have a full conversion. You can think, of course, that when we do not have a full conversion, we still have elements which are not really bound in the perovskite crystal structure and have the ability to still move within the film. And having, of course, this insulating material at the interface will further make it hard for the charges to be extracted and might be a leading cause to see this effect of light soaking. This was not the only argument or the only reason, let's say, we had to believe that it was really mobile ions that caused light soaking. We also measured temperature-dependent VOC. So in this experiment, what we did is we had the cell on a chuck where the chuck's temperature was varied from 15 degrees to 35 degrees. And at each temperature, we saw how the VOC changed with time. So here you can see that it's really a temperature-dependent process, and that the higher the temperature, the faster the stabilization time of the VOC. So heat can also activate this light soaking phenomenon. Now, by applying the same methodology by Lin et al., where we would use an Arrhenius fit, we could get an activation energy for this light soaking process, which was found to be 0.76 electron volt. And by comparing this to the literature, we found that it was actually in the range of that of iodide migration. So these 2, let's say, experiments gave us reason to believe that really we have an issue of having a high density of mobile ions, which is very bad, of course, on the long-term on stability. So how can we find solutions for this? But even before making solutions, what are also the other losses that we have in the device? And here, this reminds me of a small anecdote that I could maybe share. I think 1 year ago, we had a project dinner with one of the partners, and at the time I met with one of the colleagues, and I asked, because I think at the time this partner had made record perovskite silicon tandem solar cells, which I found really impressive. And so I asked, how do you get these records? And I remember it was actually Eike Können from AZB. So Eike, if you're around, shout out to you. He said, it's very easy to make records. You have to do 3 things. So 3 easy steps. You have to reduce losses in VOC, in fill factor, and in JSC. So I propose that we look at this in the next few slides. What are first the losses in VOC? So in terms of VOC, we have losses due to non-radiative recombination and losses due to selectivity. In terms of non-radiative recombination, we can do photoluminescence measurements from which we can extract the quasi-Fermi level splitting, or alternatively labeled the implied VOC. So here we had different stacks, a stack until perovskite, a stack until C60, and then different layers, functional layers, to understand the impact of different interfaces on the non-radiative recombination losses. So here in stack number 1, we found an IVOC of 1.22 volt. And then by comparing this to the radiative limit of a perovskite with this band gap, so the band gap of 1.67 in our film, we can extract the losses which are due to the non-radiative recombination in the bulk and at the interface with the HCl. And this was assessed to be 160 millivolt. In the second step, by adding the top interface, so the C60 interface, we assessed an additional loss of 110 millivolt. And so by adding the different functional layers, we found that the total amount of non-radiative recombination was 300 millivolt. Now let's compare this to the selectivity losses. Selectivity losses are based on the fact that we have a certain IVOC in our device, and then the VOC of the device is lower. So the IVOC minus VOC, or let's say the quasi-Fermi level splitting of in the whole tandem cell minus the VOC of the cell, gives us an estimation of the selectivity losses. How do we get this? We can measure PL-based IVOC imaging. In this method, we have, let's say, our tandem cell, and by using specific laser wavelength, we can have a subcell selective measurement. So for example, to get an idea of the IVOC in the perovskite subcell from the tandem, we can use a blue laser that will only excite the perovskite subcell, and this gives us an indication of the IVOC in the perovskite subcell. We can do the same in the silicon subcell, and then we get an idea of the IVOC of the whole tandem, and by comparing it to the VOC of our device, we see that the selectivity losses are really minor compared to the total non-radiative recombination losses in the perovskite top cell. So this is what we have to target first in order to have the largest gains in VOC. Second, with regards to the fill factor losses, and more particularly the transport losses, we used suns-VOC measurements. So what are suns-VOC measurements? It's based on the fact that we vary the illumination intensity, and at each illumination intensity, we extract the VOC of the device, of the tandem solar cell. Now, since the measurement is carried out in open circuit conditions, there is no current that is flowing through the cell, and therefore, the curve that we construct, so the suns-VOC curve, or what is also called as the pseudo-JV curve, is the same as the JV curve of the tandem cell, but without any series resistance losses. And so coming here at VMPP, we can determine that the voltage drop at maximum power point gives us an estimation of the lumped series resistance, which is 9 ohm centimeter square. What we can also see is extract the value of the fill factor of this curve, so the pseudo fill factor. And this tells us that our device, our current architecture, has the potential to achieve 84% fill factor if we reduce the losses due to transport, so transport in the perovskite, contact resistance, and series resistance across the different functional layers. So this, now we discussed about VOC and fill factor. What about the JSC? So in JSC, we have losses due to parasitic absorption. So let's say light incoming and getting absorbed by layers other than the perovskite and the silicon absorber, and current mismatch, because we're currently in a two-terminal tandem, so it's a series connection. The cell that has the lower current will limit the JSC of the device. So we will look first at parasitic absorption. So as I said, we have the light which is incoming, and we want to reduce as much as possible light which is being absorbed in these layers. So we carried out UV-vis measurements, so reflection transmission, from which we can get the absorptance, and by comparing the different layers, C60, tin oxide, and ITO, we observe that the highest parasitic loss is in the C60 layer, which really takes away a lot of the useful light that can otherwise be effectively used by the perovskite. And in terms of the current mismatch, so I don't show this here, but we carried out spectrometric analysis, which showed us that the cell that is currently limiting the device JSC is the silicon subcell. So what can we do after we have this thorough characterization of our device? We can then compile all this data and use it or insert it, or let's say implement, feed it to a certain simulation software that allows us to derive what are the next optimization steps. So this is what was done by my colleague here, Christoph Messmer, using Centauros TCAD. He was able, using the extracted device characteristics, to have a very nice fit of our experimental device. So here you see it in green, and then the simulated curve is in orange. And you can see also a nice fit between the experimental optical data and the simulated one. So as I said, you can see that the silicon is currently limiting the JSC, and therefore the JSC is 20.2, because it's set by the lowest subcell. You can also see that the C60 really has a high parasitic absorption, and this in a second step or in a last step allows us to, let's say, derive how we can optimize our device. So now that we have made this model, we have reached the state, what we can start to do in a final step is remove the constraints which we have put in order to see every loss channel, what can it bring us in terms of efficiency improvement. So this allows us to construct such a graph where, starting from our experimental device with 26.7%, we have different loss channels, and we can directly say, okay, if I want the highest efficiency gain, then I need to tackle this issue here, which is non-ideal ETL, for example, as we saw, perovskite C60 interface. And from this, we saw that for our device, the highest losses were at the ETL interface and the series, or let's say the lumped series resistance. Also, by cumulatively mitigating all the losses that we have in the device, we saw that a practical efficiency potential could be achieved with a value of 39.5%. So now we talked, I think, about a lot of issues and challenges. What about finding solutions? So in order to reduce the mobile ion density that we talked about and improve the conversion, we turned our attention towards additive engineering to tune further the perovskite crystallization. And in particular, we used a very strong Lewis base that you can see here, which is urea, which can easily coordinate with lead iodide during the perovskite crystallization. And as a result, we observed that we had really a large improvement in perovskite in apparent grain size. Also at the interface, where we had a lot of lead iodide at the interface, we started to see that it became much more neat. These improvements in structure and morphology were directly reflected in the optoelectronic quality. So here you can see again from quasi-Fermi level splitting or IVOC measurements of the stack until perovskite. We have here the reference, and then you have here, let's say, different films with different urea concentrations. With the optimum concentration, we can get up to a 30 millivolt improvement in IVOC. Now, to our surprise, we saw that the impact of urea goes beyond the absorber. So when we measured IVOC for a stack until C60, as we have observed before, in the reference case, we have a high non-radiative recombination, so 110 millivolt drop. But when we observed that, or when we measured that for the urea case, there was a big change. It was reduced to only 25 millivolt. So urea not only acts on the perovskite morphology and grain size alone, but it also has an impact on the interface. Now, how does this happen and why? To understand this, we will start to go in two steps. First, what is the impact on the crystals? How did the perovskite grain size increase? Then we would go to the interface. So in terms of the perovskite grain growth, in order to understand a bit the mechanism, we try to track the different phases that evolve during the different fabrication steps. So here you can see the lead iodide, cesium iodide evaporation. After we evaporate, we have a relatively yellow film, as you can see, dominated by lead iodide. We have a strong peak here in XRD. We have no photoluminescence response because we don't have any photoactive phase. Now, if we solution process the reference solution without any urea, so you can see this also in real time here in the videos. The color stays yellow. We have a delta perovskite phase that appears, and we have a small photoluminescence response. However, if we spin coat the solution with urea, we already see, as you can see here in the video, that the film becomes brown in color even before going to annealing. And this is reflected in the fact that we don't have any delta perovskite phase, and we have a strong alpha perovskite phase presence prior to the annealing, which is seen through a strong photoluminescence response. So having these, let's say, different measurements in mind, we hypothesize that the ability to form the alpha perovskite phase prior to the annealing gives us the chance to have crystal growth and nucleation before the annealing step. So we already form seeds, which then lead to the growth of larger grains during the annealing step. So this is with regard to crystallization change. What about the change on the interface? Here we checked the surface property of the perovskite films without urea and then with urea with different amounts. And what we observed is that with increase of urea concentration, we start to have some stripes. As you can see here, some dark stripes that form on the surface. This can also be seen in AFM measurements. So on reference, we don't see anything, and here we see some stripes. And this gave us, let's say, reasons to believe that besides the crystallization that takes place, due to the fact that urea cannot really take part of the crystal structure, it is expelled to the perovskite surface. And as we know, when we have perovskite in proximity to C60, it leads to the creation of in-gap states where defects, or let's say where charge carriers can be trapped. And if we have enough distance between the charge transport layer and the perovskite absorber, we can eliminate these states. And this is what we think urea does. So it leads to the local separation between the perovskite and the C60, which then minimizes non-radiative recombination, as we have seen in PL measurements. Now, how did these, let's say, simultaneous changes have, or what impact did they have on the device? So again, we measured suns-Voc measurements, and here we saw that the series resistance was reduced for the device with urea because of the large grain growth and the improved conversion. And in terms of mobile ion density, we observed that devices with urea had a lower mobile ion density. And in solar cells, we actually observe, we observe that there is no more light soaking effect that is present. And in terms of efficiency improvement, so here you can see the device architecture, also the VOC fill factor, JSC, and efficiency. And both in forward and reverse scans, you can see that the efficiency was improved with up to 2% absolute, mainly due to improvements in VOC and in fill factor. So now we discussed about the absorber, and we will try to quickly go over how other parts can be improved, such as the whole transport layer, especially taking into account the need for conformality on textured silicon. And here I will make the attention or the focus on self-assembling monolayers. So self-assembling monolayers have been introduced first by Artyom Magomedov in 2018, and they are a family of materials which have a similar structure. We have an anchoring group that covalently binds with the metal oxide. We have a spacer group and a terminal group. And they are really magical, so they work very well on planar, on textured substrates, but sometimes they do not really form as good as we want them to. So sometimes we can see defects such as tilted or misaligned molecules. We can have other types of defects like non-covalently bounded molecules, so not having only one monolayer, but multiple monolayers. We can also have agglomerated molecules in solution, and we can have non-full coverage, so having boundaries. And what we asked ourselves is how can we use temperature as an advantage to tune the formation of SAMs? As we saw earlier, temperature can really help in tuning the crystallization process of the perovskite, but what about doing this for the SAM? And as a methodology, we used in situ X-ray photoelectron spectroscopy, and we use as a SAM 2-packs. So we tried to track, so let's say in practice, we spin coated the SAM, and then we took it to a chamber where we then did the annealing variation, and it was in a controlled atmosphere, and we saw how the XPS spectrum changed, let's say, depending on the time and the temperature. And in terms of analyzing the data, we used the scattered electron background analysis by my colleague here, Stefan Lange, which enables us to get from the background an idea about the thickness of the SAM. So by doing this variation, so here you can see an uncoated reference doesn't have any SAM. Here we have SAM annealed at different temperatures. You can clearly see how the background really changes with annealing temperature. And by extracting a value for thickness, you can see that at 100 degrees, so here you see it, the in situ annealing series, but also XC2 in order to confirm the trend. You can see that at the standard temperature that is used in literature, which is 100 degrees, we don't have a monolayer, because a monolayer of 2-packs would be around 1 nanometer, but here we have around 4 nanometers, so it's not present as a monolayer. But by increasing the annealing temperature, we saw that the thickness, the fitted thickness, really decreases towards a monolayer formation at around 150 degrees. Not only the SAM thickness was changed with the annealing series, but there were also changes in the work function and in the HOMO level. So from KPFM measurements, you can see that let's say the shift of the work function was more than 0.2 electron volt at higher temperature. And also when we did photoelectron spectroscopy measurements in air to assess the HOMO level and compare it to that of the valence band maximum of the perovskite, so to get an idea a bit about the alignment and how it changes with the annealing temperature, we saw that the delta in energy between this level and this level was really reduced when we started to go to higher annealing temperatures. So not only the thickness changes, but because the thickness changes, we then have changes that happen in terms of the orientation of the molecules, and therefore this influences the work function and the alignment. And in terms of the interfacial quality with the perovskite, we again used PL measurements from which we extracted IVOC. And here you can see that again, with higher annealing temperature, we had a higher PL intensity, which was reflected in around 15 millivolt increase up to 150 degrees. And in terms of photostability, we tried to track the PL over a duration of 300 seconds. And here we observed an optimum with around 125 or 150 degrees. There was much less change compared to 100 degrees. So how was this reflected in tandem solar cells? Here we observed that, so here again, 100, 125, and 150, and we were able to observe up to 1.3% improvement absolute in efficiency. And this was also reproducible from multiple batches, and this was mainly due to somehow an improved fill factor, but more importantly, an improved VOC. And so as a result, this was, let's say, one of the first batches where we then were able to have a 30% efficient cell with urea modified perovskite and 2 packs annealed at a high temperature. So now, before concluding, I would like to talk about the one other and last topic, which is stability. What happens if you put this cell outdoor? Does it survive or does it not survive? And can, let's say, implementing a passivation layer at the top interface help with this issue? So here I show you, it was a work that we did with KAUST. Here I show you the cell pre-test, and I show you the cell after the test. And feel free to write in the chat if you think that the cell survived or not. I can already say that it was not looking very nice. So here I can show you the variation in power output, JSC, VOC, and fill factor over around 2 months. And you can also see that the variations in temperature, where it rose up to 42 degrees. It was pretty hot. And you can see that, already in 3 weeks, we had a major degradation in power output, which really correlated well with the major degradation happening in JSC of the device, not really the VOC. So you can see that the VOC was pretty consistent over the time. And in a second place, the fill factor was also degrading. I will not hide it. It was not a very nice day for me. I was a bit sad during that day and tried to find, okay, what are the solutions? Here you can see me in the office that we can find for this issue. And I think it should start first with trying to find why this happened before finding a solution. And here we had one hypothesis. If you remember, we talked about the urea modified perovskite and having the stripes on the surface. And we thought that we might have in these, let's say, types of perovskites, a higher chance of, let's say, or a higher probability of having an interaction with water molecules, because both molecules are polar in nature. And to test whether this is true or not, we measured contact angle. So we had a droplet of water on urea modified perovskite and reference perovskite. So this is here textured silicon, ITO 2 packs perovskite. And on the reference perovskite, we saw that actually the contact angle did not change too much in value. So it stayed relatively constant. But when we did this experiment on urea, it had a much higher, let's say, tendency to go to absorb on the surface, as you can see how the water contact angle changed. And so here the solution that we came up with, or the hypothesis that we came up with, is maybe we can try to wet chemically deposit on top of the urea modified perovskite. We can solution process a certain solution that has a, let's say, a robust ligand, and the solvent can already wash away the urea from the surface and replace it with, let's say, this robust ligand that can act as a passivation between the perovskite and C60. And here I have to say it was a nice day when we came up with this hypothesis, and we were confident because we saw a rainbow. Whether this helps or not, we will see. So in terms of efficiency, we actually observed that the proposed interface passivation allowed us to further raise the efficiency of the cell for up to, let's say here, stabilized 31.6%. But in terms, and more importantly, in terms of the stability, so here again, you can see in dark, the control device. We started to see in red here for the target device, a better resilience or a better resistance towards JSC degradation. A similar pattern in VOC, again, better resilience towards fill factor degradation, and as a result, the lifetime of the cell was a bit more extended. Now, of course, let's say we still have major degradation that is happening, especially in the beginning of the test. We think that it might be still due to the fact that our absorber can be further improved, but already we can see that, let's say, it gave us indication that when we try to modify the absorbent, it leaves remnants at the interface. This can be, it might be, while it's good for efficiency, it might be problematic for stability and has to be taken into account. And this already brings me to the outlook. So I tried to cover a bit different developments that we had for fully textured tandem, and putting them a bit in the context of the development of fully textured tandems. We see that really, so in the beginning, the first few years, there was maybe 1 or 2 devices per year, but in the last 2 years, there was really a lot of research groups started to work and to realize the potential of this architecture, which is industry compatible and also has the potential to go towards higher efficiencies. And one major, let's say, takeaway for me, let's say, in this journey of development was that it's very important to not necessarily say, let's reach a certain efficiency and afterwards look at stability. It might be interesting to already, since the beginning, optimize for stability and efficiency hand in hand at the same time. And with this, I would like to, I'd like to thank all the amazing people, so both at Fraunhofer ISE and collaborators which have helped to make this work possible. And I would like to thank again the organizers and all the audience. Thank you for listening. I also put some summary slides here.